Very much. And yeah, my name is Kento Kawaharazuka, and I'm an assistant professor at JSK Robotics Laboratory in the University of Tokyo, Japan. And I'm truly honored to have this opportunity to share my research with you all. So let's start my talk. The first, our lab, JSK, has made a significant contribution to the human-like embodied intelligence, so especially in the humanoid community over many years. So first, we have worked on the life-sized humanoids like a PR2 and HRP2 for daily assistive tasks. PR2 is able to go to Subway to buy a sandwich, and HRP2 can transport a cart loaded with items. The second, we have developed Jackson, the high-power humanoid robot capable of dynamic motions such as playing tennis, the batting, the punching, and also the roller skating, and even underwater walking. And third, we have created a flying humanoid that can alternate between flying and ground mobility. And also that we have developed a modular transformable humanoid with attachable and detachable arms and legs. Fourth, we have developed the musculoskeletal humanoid that closely mimics the human body. Here today, I would like to focus specifically on this area that I have dedicated the most effort to, that is the tendon-driven musculoskeletal humanoids. And this research has often been conducted with the goals of understanding human motor abilities, incorporating human physical advantages into robots, and ultimately creating the ideal humanoid. In other words, it explores how to realize human-like embodied intelligence from hardware to software. There is a long history of the musculoskeletal humanoids in JSK, and our journey began with a spine. So the first robot with a spine was Kura, the 1999, and although it was a very small humanoid. And the next one is Kenta, the world's first life-size musculoskeletal humanoid. And then the Kotaro, the Kojiro, and Kenzo were developed using the emerging 3D printing technologies. With gradually increasing the motor output, these robots became capable of standing and performing dynamic motions. Then the next generation robots, the Kenshiro, Kangro, and Musashi, they were developed using metal machining and sometimes metal 3D printer instead of the fragile, the plastic 3D printed parts. I can show some of these robots, and this is Kenta, the world's first life-sized tendon-driven humanoid equipped with a spine, and it has 40 motors and 12 spherical joints. And here you can see the Kenta runs how to swing more dynamically than using the genetic algorithm. And next one is the Kojiro. The motors have been upgraded, allowing for the higher torque and powerful motion. Some parts of the body incorporate non-linear elastic springs, enabling variable stiffness control directly through hardware. This allows Kojiro to perform dynamic, force-intensive movements like mochi pounding, as well as the movements requiring wrist flexibility and snap, like playing traditional Japanese wadaiko drums. Aiming for more human-like body, we have developed the Kensho. Here we utilize the metal machining, metal welding, 3D metal printing, and sometimes lost wax casting instead of a fragile plastic 3D printed parts. And Kensho features a human-like thorax, collarbone, and scapula, and has the same number of vertebrae with human beings, with robot. And the next is kangaroo. The kangaroo has a human-like thorax, the collarbone, scapula, and humerus. And the most remarkable feature of the kangaroo is its ability to sweat. And when the robot drinks the water, the liquid flows into the interior of the upper arm, made of a special biporous metal structure. And when the motors heat up, the water evaporates from the metal. The cooling the motors via evaporative cooling, essentially allowing the robot to sweat. Also, this robot contains 124 motors inside throughout its body. Can you imagine that? While a typical humanoid robot has around 30 motors, but the kangaroo has 124 motors. And all 124 motors must be coordinated to move seamlessly. But even so, the human body is far more complex rather than kangaroo. And the fact that humans move so smoothly despite the complexity is truly fascinating. Then the fully modularized musculoskeletal humanoid, the Musashi, was developed. And amazingly, the Musashi can even drive a car, a form of autonomous driving. It uses both arms and legs to operate the steering wheel and accelerator, navigating through curves with running-based controls. So now we are currently developing the next musculoskeletal humanoid after Musashi. And while I won't go into too much detail yet, but this new robot will have more human-like muscles with volume as well as joint capsules, tendon, and ligaments, creating the body even closer to that of a human. So, but why the musculoskeletal humanoids? There are a lot of fascinating features in human-like embodiment. And first, the human-like proportions. Of course, by having a human-like body, they can easily adapt to environments designed for humans. And second, human-like actuation or muscles. With actuation similar to that of humans, we can directly implement human reflex mechanisms in the robot and evaluate their effects. The third, muscle antagonism. Through the antagonistic relationship of muscles and nonlinear elasticity, variable stiffness control can be achieved in the hardware rather than in software. Lastly, the muscle redundancy. This allows for a robust body that can continue functioning even if one muscle is ruptured. So this was the story of the musculoskeletal humanoids, but at the same time, we are not solely focused on them. We are developing the various robots that leverage the advantages of muscles, the defining feature of the musculoskeletal humanoids, but are not limited to the biomimetics alone. Here I will introduce one of them, the cubics, the right one, and utilizing the flexible wire arrangement, one of the advantages of wires. This robot is a mobile tendon-driven robot cubics, and we can attach and detach the 8 wires of the robot inside of the robot, and anytime and anywhere. So there is 8 wires around there, and we can construct a tendon-driven robot in building, nature, and so on by attaching and detaching the wires anywhere. And also, the drone is attached at the tip of the wire, and the drone hooks itself onto the trees or this kind of the building structures. And it is the once attached, it powers down, and cubics pulls the wire, and this allows the robot to float in the air as a wire-driven robot, enabling it to perform tasks. By changing the wire arrangement, by changing the embodiment, so the force and velocity capability of the robot can be changed freely anytime and anywhere. Then what happens next? So cubics combines with the vacuum cleaner to perform cleaning tasks. By attaching the different tools, the cubics can take on new tasks. Then, so what would happen if the cubics combined with the quadruped robot? So there is a Goan trapped under the debris, but it needs rescuing. Then the Goan with cubics approaches the scene, and drones take off from the cubics. First, 2 drones lift off and attach wires, followed by 2 additional drones hooking onto wires as well. As the wires pull, Goan is lifted into the air. Then the legs, originally used for walking, begin to function as manipulators. By using these manipulators, the debris is cleared and the Goan is safely rescued. I mean, this robot can change the embodiment, gain a new body structure, enabled to use the legs as arms. So this is just fun, but lastly, let's see what happens when the musculoskeletal humanoid Musashi combines with cubics. Yes, when the combined, the cubics Musashi uses its 8 wires to lift itself from a prone position. It's fun. Yes. Also, the Musashi, they can even perform a mid-air kick. Yeah, showcasing the unique capability that we cannot, the human beings cannot perform. Yes, thank you. This is a summary. The musculoskeletal humanoids have the human-like proportions, actuation, muscle antagonisms, and muscle redundancy, and these features greatly contribute to the human-like embodied intelligence. Also, by utilizing the wire-driven mechanisms, non-biomimetic, but the robot can change its embodiment through the flexible wire arrangement. Thank you so much.
Thank you very much. Amazing robots. Incredible. I see a very simple, fast question. So maybe I can ask you now. Someone is asking how much weight can the Cubics robot carry?
Cubics can carry currently up to the maybe 30 or 40 kilograms. Yes.
Okay. Excellent.
Yes, so each wire can exert the currently 25 kilograms. Yes, so there is 8 wires. Yeah, if we use at the maximum, maybe the 100 kilogram is possible. Yeah.